So you have a taste of what my students have usually. So I teach a class of 400 students, and the way to keep them quiet is just to stare at them. And then just to look at my watch and just keep staring. And at some point you see this. All right, okay, good morning. Welcome to round 3. We didn't finish the story yesterday, so I'm going to try to finish it because I think it's important, and it also gives you really example. I will give you some examples of where you see this really highly nonlinear, even non-homogeneous type of dissipation potentials. But let's do a bit of a recap. So this is a recap for jump processes. Okay, so what do you remember? Nothing? Yeah, Dario remembers nothing. Yes.
Oh, you established somewhat continuity equation there?
Okay, there is a somewhat continuity equation. So we end up looking at, okay, maybe just slightly before continuity equation, we have this TT, which is our semigroup. And the TT has a generator. Some people were telling me that Q is not good. Right? They say L is the generator, Q is not the generator. But I'm going to keep using Q. So then we have Q, generator. Okay. And we have, under the assumption that Q, or equivalently TT, satisfies detailed balance. So what this means is that there exists some measure pi in P of omega, for which Q of xy pi x is equal to Q of yx by y. Right? So this is detailed balance, and we denote it by pi, detailed balance condition. Then we expect our evolution, so dt of rho is equal to Q star of rho, to be a grain flow. Okay? And then the question with respect to what, and so on. Now we know that our energy, so let's start by defining our state space. Our state space was P of omega. Our energy was the relative entropy with respect to pi. And now we're looking for some R. So the question is R star. What do we take? Okay, and then we started to make this computation on the board that ended up with this continuity equation. So dt of rho plus the divergence of j is equal to 0. So this looks very familiar, pretty much almost the same as the continuous setting, where divergence here, j applied to the point x, is the sum in y of omega of j xy minus j yx. So j is an edge function, rho is a vertex function. Okay, and then we had also, so this is our continuity equation, and then we had also a kinetic relation. Does anyone remember the kinetic relation? So this was a relationship between j xy is equal to
delta u.
Yeah. And then we had this object, right? So Q of x, y, pi, x. All right, so now the question remains, can we write this guy in the form of some minus d2 of r star of rho of minus d of f of rho? This is what we want to have. That's the question. Right? Okay, and I'll give you two examples. First example is by mass well, I would say Maas, Milke, Chung et al. So they appeared around the same time. I don't remember when, maybe 2011? 2011? Yeah, 2011. And they took, of course, the state space is the same. They took the same energy. And the R and R star was given by something quadratic. So which means it can be given by an Onsager operator. And well, maybe I define the R star directly. So R star of rho and psi takes the form, I want to be careful with my, I'm gonna write down a half of a fourth, I think. Yes, a fourth. Okay, let me look at my notes because there's always this game of just numbers. A half and the R. Yes, okay, so indeed the fourth. It takes psi, I don't know why I wrote an integral. There should be a double sum. So xy and omega. Psi xy, so that's an edge function squared. Remember, what I want to have is kind of a functional for which its second variable acts on edge functions. So it takes edge functions and maps to edge measures, if you want. Okay? These are so the force to flux. And then there is this m log of how should I write this? Okay, so q x y rho x, q y x rho y. Okay, so what is m log? M log of a and b is equal to a minus b log a minus log b. So this is the logarithmic mean. Okay. So this is what they took. So it's a quadratic form. The only thing that is somehow slightly strange is this m log in the middle. So why was this necessary? I mean, we can think of, again, we have multiple points, and we have this type of graph structure. You can, like I said earlier in my first lecture, the R refers to something like friction. So it's like a friction energy, friction. And it should encode some kind of dissipation when you're moving stuff. So this functional should be an edge function because this is where stuff gets moved. Right? So what you want the functional to do is you need to pay a cost when you're in fact moving, but the cost that you pay is relative to the vertex functions, the densities that you have on the vertices. So what you have to do is you kind of have to first find a way to interpolate the vertex function. You need to map vertex functions onto the edge, and then use that as a kind of a weight in your cost for moving stuff along this edge. So this is somewhat how you should see it. Okay, and why they take this is quite simple. I can show you in a bit, but let's try to take the derivative with respect to psi.
Can I also ask something? So I was not used to see it with the raw, but if you write in terms of u, it's even more explicit, right?
Yes, indeed. So, okay, this functional does not require rho to be absolutely continuous with respect to pi. Obviously, if the relative entropy is finite, then it is absolutely continuous with respect to pi, in which case, so if rho is equal to u pi, then this formula takes something easier. So let me do it on the side here. M log of q x y rho x, q y x rho y is equal to m log of u of x q x y of pi x, u of y q y x of pi y. But these guys, this one is symmetric, so that these two are the same. And if they two are the same and m log is one homogeneous, I can just take it out. Okay? So this is the same as m log of ux, u sub x, uy, and qx pi x. Okay? So it does simplify. Thank you.
Thank you.
All right, so now what we want to do is we want to take the derivative, d2 of r star of rho and psi. And what do we end up with? Let me write here. We end up with 1/2 of psi xy times m log of that quantity. Let's take this one since it's already there. Qxy pi. Okay, so now what I want to insert here, because look, I want to be able to insert some derivative. Yes, so derivative of this driving energy, and the derivative, this is the flat derivative of rho is nothing but log of rho over pi, which is also, if rho is u times pi, this is nothing but log of u. Okay, so hence, let me write here, hence d2 of r star rho minus d of f of rho is equal to 1/2 of, so instead of psi, I'm going to put a minus here, that thing over there, of log of u at the point xy times the logarithmic mean of u of x, u of y, q xy phi x. Okay, so what is the discrete gradient of the log? It's nothing but 1/2 of log of u of y minus log of u of x. What is the logarithmic mean? That's just u of x minus u of y divided by log of u of x minus log of u of y. Okay, and then you see some cancellations. Okay.
A sign which is not, because you did log of u of y minus log of u of x, but maybe it's the opposite.
No, this is fine.
Okay.
Yeah, it's fine.
Okay.
So, let me see. Is this fine? It should be fine. Did I put the minus too much?
No, the minus is solved. That's exactly right.
Yeah.
So, this is going to be u of x, so 1/2 of, maybe there was a sign. So this one I'm going to cancel with that, but incurring a negative sign. The negative sign is going to cancel. I get u of x, u of y of qxy pi x. And what is this quantity? That is nothing but minus 1/2 of u of xy, qxy pi x. Yeah? Okay, so we end up with pretty much the flux. This is our J. Xy. So it works. Yeah? Magic. Why? Well, what was the real idea here? The brilliance here is simply this. So the problem about in the discrete setting is that you don't have something looking like this. The gradient of the log of u is equal to 1 over u, so maybe more like, yeah, the gradient of u divided by u. This is something you do not have, right? Or maybe another way of saying this is something you do not have. So what you try to do is you try to replicate precisely this in the discrete case, right? By doing this. By artificially kind of putting a chain rule, a discrete chain rule.
Actually, the quantum world is better to explain discrete differentiation, I think. If you use the quantum calculus,
yeah,
this explains why you have to do this kind of differentiation better.
Well, in fact, you don't have to. So I will show you a nonlinear structure.
I mean, what happens, I mean, that is this language of bimodules, and that explains where this comes from.
Oh, okay.
I mean, I'm saying there is, the discrete world is, in this quantum world, is even a little bit more natural.
Okay.
But of course, this assumes that you understand some of this quantum calculus in the first place, and that can be argued with.
Yeah, I mean, I think if there is a good, so at the moment I don't have a good motivation for why, except for the fact that you need a chain rule like this. Okay, so I would be interested in seeing this. So I will show you another structure, which is a nonlinear one, the one I kind of promised. This is 2. This is by Pelletier et al. Also with, so this is Pelletier, Michiel Renger, Alexander Milke. I think Matthias Lero was also involved. This is around 2013, something like this. No, even later. It is later. But they came up with a structure. So the R star takes the following form. R star of rho of psi is again 1/2. Keep forgetting. So double sum xy of omega. And I'm just going to write here psi of cosh of psi xy m geo of qxy rho x and qxy yx rho y. Okay, so what is this psi cosh? Psi cosh of some r is 4 times the cosh of r over 2 minus 1. And the m log of a and b is simply the geometric mean between a and b. Thank you. Geo, yes. So this is a different way of making vertex functions into edge functions. It's an interpolation between the two. But then the cost here is nonlinear, non-homogeneous, and it's of exponential form. Okay, so this structure, although it looks funny and you may think, so why? In fact, this has a longer history than this, much longer. This already exists for people in doing chemistry from way back when. Yeah? And in fact, this was derived using a large deviation principle, and they found the structure using a large deviation principle. So LDP motivation. So let's see the calculus a little bit. Let's take the derivative of 2 of r star of rho of psi. What is this? This is, I have 4. I'm going to multiply with a half, I get a 2. And then if I apply the chain rule to the cosh, I get another half. So I end up with just sine h r of 2. And then I'm going to multiply it with, sorry, that should be psi xy. So this should be a function of xy, of course, as before. And then I'm left with my mgeo of, so let's write ux uy now, of qxy by x. Pretty much as before. Okay, so now let's insert our logarithm, so the derivative, into this quantity. So we d2 of r star of rho of minus nabla log nabla d of f of rho is equal to, so of course this again xy, this is equal to sine hyperbolicus of minus log of uy minus log of ux over 2. That's what I just did. And then we have a square root of ux uy. I'm going to drop this last term just for simplicity. I mean, I don't want to write it, but it's there. And then we have, I'm sorry, Dima, I need to maybe write here instead. Yes. Okay. Thank you. Then we have, so I'm just going, so that's the same as log ux minus log uy over 2. I'm going to put the over 2 into the square root. So there's going to be the log of the square root, and then I'm going to use the sign. So then we have a half. The sign is e to the log of ux uy square root minus e of minus log of square root of ux uy square root of ux uy. Yeah, okay, let's write it just for completeness. And then you see again, e of the log, I get just 1/2 of ux uy minus, I flip this around, uy ux, square root of ux uy. Then you multiply them, so you get ux square root, so this is 1/2 of ux minus uy and q of xy by x. So again, you get 1/2 of the discrete gradient of u of xy, q xy by x. And this is the same as j of xy. Okay? So these are two structures that give you, so here again, we have the same energy. We have the same space. We have the same equation, but different dissipation potentials. The change is what the cost is to actually transmit from, well, essentially the cost on the edge of moving mass on the edge. Questions? No? Okay, so which one would you use? Would you choose one over the other?
It should depend.
Sorry?
It has to depend, right? I mean, you You have to have a reason.
Indeed, you have to have a reason.
Sometimes if you know one better, that's the one you choose. but
But
I don't know what reason.
Okay, indeed, it depends.
Oliver, but is the choice only among these two, or you can?
There's a whole family. I mean, in fact, you can. We in one of our papers we took simply for simplicity something that looks like this, something like a half of, pretty much like the form I wrote down there, right? So x, y, and omega psi of psi xy, and some m of yeah. And this type you can find so many families, a whole hierarchy of them. And if you can find two, that means the chances of you finding infinitely many is very high, right? So.
Does that characterize all of them?
No. So I have yet another paper. This is it comes from doing numerics for aggregation diffusion equations. So equations where you have diffusion, you have external potential, and you have interaction potential. And you say, I want to do numerics for this, but I want to do it in a very smart way because my interaction potential can be singular. So what do? There is a scheme that people have been using for many years now in semiconductor where they solve this kind of self-consistent diffusion equation, something like in ion transport and stuff like this in semiconductor modeling. And this method is called the Chaffetz-Gummel scheme. When you do a discretization, it ends up being, in fact, a jump process on your tessellations. You tessellate your space, and you can write the scheme down. It becomes a jump process. And then you may think, well, maybe you can use one of the two. It turns out that you can't because, as I mentioned before, a good strategy is to try to always separate the forces from the geometry, from the dissipation potential. If you were to apply any of these two, they mingle. Right? So if you want to say, I want to prove that this scheme converges numerically to a Wasserstein-Graton flow or Otto-Wasserstein-Graton flow for the aggregation diffusion equation, then the smart thing to do, at least it's not only smart, but worse for us, the only way to do it is to find a way to split them. And so this is called de-tilting. So when you de-tilt and enforce that the forces are separate from the geometry, so the dissipation potential, then you do not end up with objects like this. You end up with something a little bit more general. You end up with something like that, qxy, yx, qyx, yy. Sorry? Thank you. You all are paying attention. I like this. Okay. Yeah, you had breakfast. Good. And in fact, you don't have an explicit form for phi or for psi. It's in some it's like a logarithmic harmonic mean of some intermixing of stuff. But then it turns out that when you do some kind of asymptotics, because you say you want to prove that it converges to making your tessellation smaller and smaller, then you do an asymptotic expansion of that, suddenly you see the Wasserstein term pop up, and all the other terms pop up nicely. So, long answer to your very short question. Yeah, no. So, okay, so I'll give you maybe one reason why I like this better than than the Maas Milke Chung version is when you look at, so if you remember, okay, a step back. Once you have this, then you can do the whole procedure as we did before. So you have the R plus R star plus the difference of the entropy. So you can write your Lagrangian down or your energy dissipation functional and you minimize it and you have this variational characterization. Now, but then what I haven't told you since day one is the explicit form of this R star, so the middle term. So we have then ST R of rho of J plus R star rho of minus d of f of rho. This is dr plus, in our case, yeah, okay, let's write down f of rho t minus f of rho s, and this is 0. Right? So this is the zero cost flow. This quantity, obviously, if I have different r's, they take different forms. Yes? And I mean, if you write down for the Jan Mas and Alexander Milke and Chung et al. Structure, then you will see, it's not here anymore, maybe close it, yes. So that's just inserting this, and we have, okay, I erased it, but we have a quadratic form. So this ends up being rho of minus df rho is equal to 1/2 of, still 1/2, so 1/4, no, 1/8, the double sum of xy, and then we have the gradient of the log of u of xy squared times m log of u x y, and then we have our q, x, y, pi, x. Okay, so this is what you get. Of course, if you see here, this is similar. So like in the continuous case, you can think that this is roughly the same as the integral of u gradient log of u squared dx. Right, you expect the Fisher information to pop up. Right? That's your... for this reason, we also call this guy the Fisher information, because the Fisher information, from at least my understanding, is the dissipation created by osmotic forces. So if you do time reversal and stuff like this, so this is the guy that pops up, so that's the Fisher information. This is the cost of moving. That's why it's R acting on J, and J is the flux. Okay? So that's the cost of moving, that's the osmotic force. Whereas if you take 2, R star, so this is, I put 2 here, and that's a cosh, rho of minus df of rho. And this is going to be something like 1/4 of the sum xy of the discrete gradient of the square root of u of xy squared q xy by x. Right? So this is roughly the same as the integral of the gradient of the square root of u dx with the square. Sorry, with the? With here, yeah, something like, yeah, I don't remember. But some constant here and here. They are different because, yeah, okay. Okay, now, which of these do you actually like?
The first one.
You like this one better?
Yes, because it's more stable for Loss-Sobolev inequalities in the quantum world. And the CLSI inequalities suck if you have non-ergodic systems. 1.
Okay.
Everybody else has 2, I know that, but
So maybe in the 3 months we can convince you otherwise. It's okay. So I like this one better. And Lorenzo Portinala at the back, he understands why I like this one better.
I'm not going to admit it, yes.
Yes. Because this allows you to do many more things better, especially when you do asymptotic limits. Also, when you do the analysis, I would say here, if you're, so in order to control terms like this, you really need a lot of PDE theory, Harnack inequality, stuff like this, whereas here you don't care. And here you can apply gamma convergence very easily. Here, this is going to be very hard. So there are a lot of good things about this structure, besides coming from a large deviation principle, than that one. Okay. But I'm also, somehow we've seen a lot of situations where this is good. So like I was mentioning, when you look at really birth and death processes on configuration spaces, passing to the limits, everything becomes so much easier in this level than that. Like you can even prove entropic propagation of chaos, all using this type of structures. Okay, so now this is essentially the end of the story for jump processes, because I would like to, how much time do I have? Not much, right? 10? Very good, okay.
Can you say anything about the large deviation principle?
So on this one, yeah, so it turns out, I think I already mentioned this to you yesterday also, but what you do is you look at, so rho n, 1 over n of, d of these guys, xi, at t, so. And then you look at j n t of 1 over n of delta of xi t minus xi t. Okay, so these are kind of the places where they jump, because t minus is different from t. This is just the density. If you do a large deviation principle for the pair, for this pair, you end up with precisely this rate function, so this rate function, with the cost structure. This is what you get.
So is that more engineered process that gives you as a large deviation approach 1? Or is it?
I don't know. So maybe something from quantum. I'm not sure. But, not that I know of. Okay. Yes, okay.
So I'm a little bit lost, but I was trying to understand. So here we saw the two examples of choosing different R star. So these lead to like slightly different Lagrangian.
Yes.
Right? But like the end equation that is like equivalent to Lagrangian is the same in both cases, right? Like
The zero cost flow is the same.
so like
the equation is the same.
you're like when you take these derivatives, as far as I see, like you still get the same kinetic relation.
Yes.
So it's
So again, this is zero cost flow, which means if I look at the zeros of this functional, then they're exactly the same. But the moment I deviate from it, these functionals will give me two different values, because they are different functionals. And therefore, that's why when I'm doing gamma convergence or whatever, when I'm actually playing with the functionals, this makes a difference, which one you choose.
okay. I don't remember if we considered the quadratic case for the equations with like j instead of just x. Like in the very first lecture, we didn't have a continuity equation of kinetic relation. We were talking about just the gradient flow, like x and the gradient of f.
Mm-hmm.
And here we also said that we could do like R and R star. I'm still not very sure like if this Lagrangian sort of like
It's the same. So what you need.
and we could still consider like the quadratic and how the quadratic would look like.
Yes. So the Onsager operator for the quadratic is precisely this guy. So you take it's a linear quantity. So this is minus log of. So this is xi so applied to some xi, and this is xi xy of m log ux uy and qxy by x. With maybe a contraction, because I'm doing the Onsager on the level of the fluxes or the forces on edges. Yeah. But there is still a, so you can think if it's quadratic, then this derivative is always the Onsager. Okay. Any more questions before we move on to non-commutative stuff? So unfortunately, I won't have time to talk about too many non-commutative structures, so I had planned to talk about two non-commutative structures, one coming from machine learning and the other one from quantum. So the one in machine learning I will unfortunately skip. So I will talk only the one about quantum. But let me say maybe a few words about the one in machine learning. So in machine learning, this gradient flow stuff has been used a lot in variational inference. So essentially, you want to kind of sample well, and you want to sample from a target distribution, and then you want to run a gradient flow, and hopefully you start sampling. Now, if I give you an energy, so maybe a measure pi, you take the relative entropy as your driving force of this gradient flow. The classical is to say I'm in the Wasserstein space, and I can do this. I end up with the equation that we saw yesterday, just the Fokker-Planck equation, and I evolve this. Now, but obviously, sampling from arbitrary measures is maybe not so easy. So what some people would like to do is to say, well, let's approximate this arbitrary measure with a Gaussian measure, a simple Gaussian measure. Now, nice thing about Gaussian measures is that they are simple to sample from, okay? Even for arbitrary covariance matrices. And moreover, they are finite dimensional. If you look at the family of Gaussian, they're parameterized by a finite dimensional space because all you need to do is parameterize the Gaussian and parameterize the mean. What you can do, though, is go from your gradient flow structure on the space of probability measures, and you say, I restrict it to a submanifold of only Gaussians. And when you do this, you can, in fact, pass the gradient structure on the big space onto the small space, along with its energy, along with its states, along with its dissipation potential. Okay? And when you do that, suddenly you find something very, very consistent, very nice. Everything is preserved in everything you want. And on top of that, you get a gradient structure. So that was the first part, yes?
So how would you see this? Should I think of this, like if I'm in a Riemannian manifolds, I want to do like a gradient flow, I have a metric, and then I kind of like have a sub-manifolds, and I try to project the gradient or something? Is it something like this? Or
something like this, something like this. Of course, there is one caveat here is that so I didn't say, but you have to assume, of course, that your evolution is going to be invariant. So if you start in that manifold, it remains in that manifold, then you can project it. But the idea is to really project the gradients. And by doing so, then you recover a gradient structure on the level of the manifold. Okay, so that's just a small story, but I think more for this group, let's do the quantum one. And the quantum one is not my work, personally. It's the work, I'm going to introduce the work of Eric Kallen and Jan Maas. Of course, Trifon has worked on this as well. Alexander Milke has worked on this as well. But yeah, let's see. Okay, you ready? Yeah? So gradient structures. For non-commutative evolutions. Okay, so this is part 3. So the starting point is again the same. I'm given a semigroup. So maybe I have to define now what I mean by a semigroup because, before I talk about a semigroup, I need to talk about my state space. So what is my state space? I'm in finite dimensional setting. I'm going to deal with matrices. So these are density matrices. So let's look at SCN. And this is my state space. This is going to be my X. And this is going to contain all the matrices, say rho in Cn, for which rho is, I'm going to use this, let's non-negative. Trace, I'm also going to assume that I have some trace, is 1. And I'm going to assume that it is self-adjoint. I'm a friend of the dagger. I like the dagger. Okay, so that's my state space. And I want to look at a semigroup on this. So I consider some semigroup And by now, so after all the talks that we've seen, especially from Dima's talk about quantum channels and stuff like this, then you kind of know that this guy for each t should be a quantum channel. So this is what you want it to be. So not this guy, but the adjoint. So t star, which is the adjoint with respect to the Hilbert-Schmidt. Inner product is required to be a quantum channel. Okay. In other words, you can also say that T is going to satisfy some properties. So let me define a quantum semigroup, a quantum Markov semigroup. T is one that satisfies one that is unital, so which means that it maps the unit state to the unit element, and two, that it is completely positive. So I don't think I have to tell you what completely positive means, because you've seen this a couple of times now. So this is the requirement of kind of a quantum channel. Turns out that if these two are satisfied, then of course it also should be a C0 semigroup in time. This is a. Okay. But then T star is going to be positivity preserving, completely positive, and it's also going to be to map. It's going to be trace preserving. Yes. These are the properties of T star. Okay, so far so good. Any questions so far? So this is our setting. We start with just some quantum Markov semigroup, which I defined. And now, obviously, this gives you an evolution. It has a generator. Okay, so in some sense, you can say that t is given by some exponential of t times, I'm going to use L, okay, some generator. At the moment, I don't want to write down the generator, because if I do a generator for general semigroups, it can look quite bad. Not bad, but still, it's more complicated than the one that I'm going to consider in a bit. Okay, so now this evolution is an evolution, but when is it a gradient flow? This is the question. Pretty much like in the jump diffusion case. When is this evolution a gradient flow? And it turns out that there is some notion of detail balance also in the quantum case. Unfortunately, this notion of detail balance is not unique. Why? Because, so remember when I defined detail balance for the jump process, I also gave you an equivalent characterization of detail balance. So recall equivalent characterization of detail balance. This is pi dBc, which was to say that that Tt of either phi, psi, or Fg, yeah, let's keep it Fg, is equal to Ftg of pi. Okay, meaning that Tt is self-adjoint, or its generator is self-adjoint with respect to this inner product, this pi inner product. Remember, the pi inner product is just the inner product, the weighted inner product with respect to pi, Fx gx. Now, in the non-commutative setting, you can also think about something like this, and you can say, well, I say that Tt satisfies detail balance with respect to Now instead of pi, I'm going to use sigma because somehow it's common in the quantum community. Sigma, yes, so it satisfies the detail balance condition with respect to sigma if something like this holds. This is what you can say. Okay? Unfortunately, here, because it commutes, I can shift this anywhere I want. I can put pi x in between the fx and gx. I can put it at the end. In the non-commutative case, this is not true, right? So obviously, if I were to define something like this, say take the trace of a dagger b of sigma, this is not equal in general to the trace of a dagger sigma of b. In fact, I have a whole family of them. I can put something like, so a dagger, you can put sigma s b sigma 1 minus s. As long as in sigma it is going to be one homogeneous. A whole family of them. And this I will define as just a of b sub s. Okay. So when I define detail balance, which one do I define detail balance with respect to?
1/2.
Sorry, a half?
You start with 1/2 and then you ask for more.
You start from 1/2 and you ask for more. So that's a good suggestion. What I will do is not that. Well, what I will do instead, so in fact you can generalize this quite a bit. So if I let delta sigma be the so let me just define it like this. A be defined as sigma a sigma minus 1. Okay, this has a name, of course. Then what you can do is you can rewrite this in the following way. So then a b of s is the trace of a dagger. So I'm going to do s here. I'm going to put sigma minus s and times sigma. So this is going to be. So this is an operator acting on matrices. Right? So what I'm going to do is I'm going to do some functional calculus, and I'm going to take the power of s of this operator. I'm going to act it on b, and I'm going to leave my 1 sigma here. Okay. And in fact, you can generalize this to say I have ab of f, some real valued function, or essentially positive value function, non-negative value function, of f of this operator acting on b times sigma. So, which means I have infinitely many, this. Right? So, it turns out, however, so there's a result of, I don't know if I'm pronouncing his name correctly, Alitsky? Okay, Alitsky. And Eric and Jan, they kind of did a modification of the proof, made the proof simpler. But essentially it says that if you are detail balanced, so if the statement is the following proposition, if TT satisfies sigma detail balance, satisfies this, which I will call sigma detail balance, satisfies I'm sorry. No. I don't care about the T. So if T, some map, is self-adjoint with respect to this inner product, S, with S between 0 and 1, without a half, okay, then it is first thing, it commutes with this operator delta sigma, and it is self-adjoint with respect to all s between 0 and 1.
Sort of just shows why 1/2 is such a special thing to require.
1/2 is a special thing to require. So in fact, there are situations where if you take 1/2 and it's self-adjoint with respect to 1/2, but it's not self-adjoint with respect to the other.
Yeah, unfortunately, people I know, they want to do only 1/2.
Sorry?
The people in quantum simulation, they only want 1/2.
They only want 1/2.
Which sucks, I mean, because the other ones are much better.
Yes, this is true because, I mean, if you say I satisfy detail balance with respect to, say, the 1, or in fact, all of this has a name. So S equal to, let me see, S equal to, how did I define it? S equal to 0. This is GNS. This is Gelfand, Naimark, Segal. S equal to 1/2. You know what this is? This is the KMS. And there's another one, which is very interesting. There is also the BKM. And this one you've already seen. So let's do A, B. You've seen it because Trifon showed you very quickly. And this is equal to the integral from 0 to 1 of them all. This is Bogolyubov, Kubomori, exactly. The same Bogolyubov that Kasia mentioned from the BBGKY. Okay, so this guy turns out to be also a very nice tool, and this guy is the one that we will use, or that Jan Maas and Eric Carlin used to give a gradient flow structure to what we will see later, because we've not even seen what the equation is. Yeah? Okay, but the nice thing is that from now on, I'm going to define my detail balance condition based on, in fact, S equal 0. Because why? Then it is, in fact, there is a bigger statement saying that if this is true for S equals 0, then it is true for any function f.
Well, not the 1/2. So how do you distinguish? Is the 1/2 the only problem? So
No, even this one. Sorry, this one also. If it satisfies detail balance with respect to this,
okay.
yeah, does not mean that it satisfies. There are examples where it will not say it does not satisfy, say, S0.
Yeah. So maybe I just confused what you just said. You said in the statement above, if you have self-adjoint with respect to S not 1/2, then you are self-adjoint with respect to all the S. You said
So this is the
all
exist.
F. No, the F, no.
So there is another statement that says all the f.
But not the 1/2. So I'm trying to understand which F you excludes.
If you have
Also 1/2. This one also includes 1/2. And this one also.
I thought it was.
With delta in common.
Yeah, once you commute, in fact, necessarily you commute with all of. I mean, like you're self-adjoint with respect all of them. Yes.
So you can often get these semigroups by dilation, right? So in the sense that you take a process of some kind and you condition the process to time 0, and that's your semigroup. So your semigroup at time t is to run the process for time t and then condition to time 0.
Okay.
Is it easier to understand when those are gradient flows than the ones than the more general ones?
I think they're almost equivalent because somehow I know that any. Okay, obviously not in the quantum case. This I don't know yet. But in the classical case, any contraction semigroup
Right.
induces a dilation,
Right.
for which.
So that's why I'm wondering if there's a better gradient structure for the dilation than for the actual semigroup.
Yeah, so the dilations are usually unitary maps, right?
Well, I mean, it's a stationary process, right? Which then you condition, so it's like an
Yes.
injection into a larger thing.
But there is this evolution going on the top, on the dilated space, which is unitary. It's a unitary evolution.
Maybe.
I mean, this is the nage voyage type of construction, no?
Can I answer that question?
Yeah.
For GNS symmetric, you can write this as delta star delta, the generator. You have dilation. You can reduce it to the tracial case completely. And in the tracial case, we know that there's a delta star delta and some dilation. So.
No, but I'm just asking in general if it's better to. Well, I mean, but you're assuming self-adjoint for that.
I'm using GNS.
But there you're assuming it's self-adjoint.
Yeah. So I think he's saying no GNS, but
Non-GNS, you can probably still do something, but it's much trickier.
okay. So yeah. Unfortunately, if I don't finish today, which means I don't finish at all, yeah? I mean, okay, so, yeah, so there's this guy. There is a nice theorem, so we will define, just saying a definition, TT satisfies sigma detail balance condition if TT of A, B of the GNS is equal to A TT of B of GNS. Okay? In which case, it's also very, very easy to show that sigma is going to be a stationary state for TT star. So here, TT star, if this is indeed the case, then of course this is for all T. Yeah? This is going to be true. Okay? So this is a very short exercise that you can do. All right, so why is all this important and nice and fancy? Is because once it satisfies this, then there is a very nice theorem by, again, Alitsky, sorry, that says that that semigroup will have a generator that takes a very specific form. So it's a proposition. It says let TT satisfy sigma dBc, then the generator, so its generator takes the form L of A is the sum of e to the minus omega j in some index set j, of Lj of A. And what is Lj of A? Lj of A is Vj dagger, Vja, comma, plus Vj dagger A Vj. Okay. My apologies. There is some. Yeah. Sorry. This is A Vj. Yeah. Okay. Or you can write also minus here if you want, because that's the commutator. All right. So this is what the statement says. Okay. So let me tell you what these Vj's and I don't have. Okay, let me take. That's what these Vj's are and omega j's. Takes where delta sigma of Vj is equal to E minus omega j of Vj. Okay? So you can think of e to the minus omega j, Vj as the eigen pairs for this delta operator. I wrote it, I keep forgetting the name. Yeah, the modular operator, yes. The sigma modular operator, yes. This is true, yes. Thank you. Yeah. Sigma modular. So of course you can write this also in the sigma modular automorphism and all this type of things, but let's, yeah. Okay. We also want to notice that this is going to be helpful, is that if Vj, so Vj is equal to Vj dagger, so the family, if I collect them all, they are the same. Right? It's just the family, not that they are self-adjoint, but somehow the indices can change. But if they do change the index, so if J star is such that Vj star is equal to Vj dagger. Also, not if, but let, yeah. No, what do I want to say? Yeah, so, yeah, okay, say, yeah, set J star is such that this is true, okay? Then we also know, because of this, right? So we say that, okay, so let's do this, d sigma of Vj. Let's take the dagger. We know that this is equal, I have to say omega j, these are real numbers. These are not complex, these are real. This is equal to e to the minus omega j of Vj dagger. But on this side, what do I get? I get somehow the reverse modular operator. This is sigma because of the dagger, and sigma is self-adjoint. So this is sigma minus 1 of Vj dagger of sigma. So this implies that delta of Vj dagger is e to the omega j of Vj dagger. Okay. So because of this, we know then, hence, omega j star is going to be minus omega j. Right? Because here I have that omega j, but because of this equality, I get that, that this is true. Okay, so this is kind of useful and helpful because this is where we're going to see how this structure becomes a gradient flow structure. Yes, this one is fine to erase. Okay, so now we have our equation. Then we can play this game. We have to define some kind of continuity equation, which means we have to define some kind of discrete gradient. We have to define some kind of discrete divergence. And we can write down an equation, and then we need to find our R star, or our on-cycle operator corresponding to this. Dimba, you look very disturbed. Tell me, what is it? Okay. Okay, so this equation that we have, so that's our generator. So this equation, rho, is equal to L star of rho. This is what we call the Lindblad equation. Yeah, where L is the generator that is here. Okay, so let's do some definitions. So we set our partial derivative of an operator simply by taking the commutator with respect to this Vj. So you can think of, once I've in the semi-group that satisfies theta balance, it turns out that there are coordinate maps somehow, right? And your Vj's are your coordinate maps.
So these correspond to the eigenvector directions.
Indeed, precisely. The eigenvector, yeah, the directions with respect to this modular operator, the sigma modular operator. So you can define this object, and in the same way you can define the dual of this object, this operator that is just Vj of A. And then you can define the discrete gradient of A, that is nothing but just partial j of A as a vector, right? J and j. Maybe I put a transpose there so it becomes a column vector. And you can also define the discrete divergence, or I won't say the discrete, but kind of a divergence in this setting that takes simply this, I'm going to put a minus the sum of j from j, and I have dj star of not A, so E should be some kind of a vector field, right? So A you can think of as a scalar quantity, and E is a vector quantity. This is E of j.
So what did you mean with the T of the vector? Sorry.
Okay, you don't have to put this. I want to make it a column vector, but you don't have to. I mean, who cares? Okay, yeah. I'm sorry for the confusion. Okay, so these are your structures. And now, in fact, what we can do is we can write down, in view of time, I'm not going to do this computation, but you can write down dt of rho to be equal to, let me see, just don't want to. Yes. So plus the divergence. This is our continuity equation. And now the nice thing is that we can write down our j, Ej. Okay, what is Ej? Ej is equal to, there is some weights. Okay, so let me see. Yes, E rho j, rho Vj, Vj rho. This is E. And to do this computation, you really need, I made a mistake. This should be a half here. I'm sorry. This one is fine, but that should be a half there. Okay. This, and then I have rho, I can't remember which side. Rho Vj, yes. Rho Vj minus e to the minus j half of Vj rho. Okay, so from here, then we can, there's this nice result by, again, Eric and Jan that says, so proposition that says that this guy takes a very specific form. I can write it, I can write this as some kind of mapping, again, that takes, I need to map, you can think of rho again as a vertex function. I need to map it to edges. But this is done by some kind of product, which I will define, of the log of rho minus the log of sigma. Okay, so when you see this type appearing, then you can think, okay, what type of energy are these guys using? They're using what they call the Umegaki energy. So this is the relative entropy of this form. So the F of rho is equal to the trace of rho log rho minus log of sigma. Obviously, this is not only this energy is nice, but it's not the only energy because of non-commutativity. You can shift all your sigmas around in every way that you want, and you get different energy, and therefore probably a completely different also structure if you want to end up with the same Lindblad equation. Okay, but this is what they do, and what is this product? This product is acting on some A. This is the integral from 0 to 1 of e to the, I don't know which one is the minus or the plus. So e omega j over 2 to the 1 minus s applied to A, e to the minus over 2 of s oh, sorry, there should be a rho here, ds. So it's kind of taking some mass with some coefficients, so with some of these eigen, I would say that more like the spreading of the mass into the directions, the eigendirections, okay, and averaging them somehow.
You can understand it as a variation of this BKM.
Indeed.
BKM
Yes.
with
So if you remember the
weighted BKM in a product.
yes, yeah, indeed. Thank you. So this is the product, and if you use this product, you end up with this form, and then from here you can already read the Onsager operator, because this guy is nothing but d of f of rho. Okay, so the Onsager operator really takes somehow, that depends on rho, because you need rho to produce this rho j hat, and then it acts on this object. Okay, and from here you can continue and kind of end up with your grain flow structure or formulation.
Do you know what the flux is? Have you calculated the flux in this situation? What before you call J, the flux?
This is the E. The E plays the role now of the. So if you look at my continuity equation, the E is the flux. Yeah. So all I've done now is kind of written it in this form. So minus of a k of my apologies. There should be a minus here. K of rho of d of f. This is, yeah. Okay. In view of time, I think I should stop here. Thank you for your attention.